Hey everyone, in this video we are going to be talking about triacylglycerols. The topics for this video will be what are triacylglycerols, talk about a fat versus an oil, talk about the hydrogenation of oils, the hydrolysis and saponification of triacylglycerols, and by the end of the video you should be able to describe the structure of a triacylglycerol and predict the products of hydrogenation or hydrolysis of a triacylglycerol. So let's take a look at the structure here. So an acyl group means a carbonyl, a C double bond O. Now tri means three, and a glycerol is a molecule that looks like this. It's a 3-carbon chain where each carbon has an alcohol attached. So this is known as glycerol. Basically propane with 3 alcohols. And so a triacylglycerol has 3 fatty acids connected to a glycerol as esters. And so the esters are, those bonds right there, and that's what connects the fatty acids to the glycerol. And we care about these molecules because this is the primary way that animals, including humans, store energy in the body. So your fat cells are full of these molecules right here. So this is what fills up your fat cells. This is the fat. It's a triacylglycerol. So how do we make this? Well, we got to start with glycerol, and we got to have 3 fatty acids, and we are going to remove the H and the OH from each one. So it's an esterification reaction, just like we saw with the waxes. Alcohol, fatty acid, ester. Now, the cartoon structure here is just showing you it's a glycerol connected to 3 fatty acids, but the actual functional group is an ester. Okay. And we lose the 3 waters right there coming out. So glycerol, 3 fatty acids, 3 esters, and this is known as a triacylglycerol. Now, we can have what are called simple triacylglycerols, and that's when all of the fatty acid tails are identical. And so here, if we were to look at this fatty acid in gray, it's a 14-0 fatty acid. The other one's also a 14-0, and the other one's also a 14-0. So those are all exactly the same fatty acid tail, and so it's called a simple triacylglycerol. But they don't have to be the same. They can all be different, and that's what we call a mixed triacylglycerol because it's a mixture of different fatty acids. And so you can see here, this is like a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. God, that took too long. So that's an 18-0 fatty acid. This one is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This one's a 12-0. And this last one here is a 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. It's a 17 with 2 double bonds. So you can see that all of the fatty acid tails have a different structure to them. So it's a mixed triacylglycerol. And not all 3 of them have to be different. You could have 2 of the same and 1 different. As long as they're not all identical, it's mixed. And as I briefly mentioned, triacylglycerols are the primary energy storage system in animals, us included. And so if you were to look at your adipose or your fat cells, they are full of little vesicles, just jam-packed full of these triacylglycerols. And so this is what a fat molecule is. And if you don't eat for a long period of time, or you go on a diet, your body starts hydrolyzing these and releasing the fatty acids, and then the fatty acids get chopped up in your metabolism, and your body converts it into carbon dioxide, water, and energy. So we store them for energy on a rainy day when we don't have food, and then we burn them up as energy. Let's talk about the melting points of fats and oils. So we typically define a fat versus an oil based on their melting temperature. If something is a solid at room temperature, we usually call it a fat. Common fats would usually come from animal sources, things like butter, lard, cheese, right? They're oily, but they're solid at room temperature. And an oil is something that's a liquid at room temperature. These usually come from plant sources, right? Like olive oil, canola oil, your typical kitchen cooking oils, right? These are liquids, whereas fats are solids. So two terms at the molecular level, they're all triacylglycerides. We'll talk a little bit more about the intricacies here, but the word fat is usually referred to things that are solid at room temperature, and oil is for things that are liquid. So let's talk about fats. So fats tend to be saturated triacylglycerols, meaning that all of the fatty acids in those three tails are saturated. So just like the melting points of the fatty acids themselves, if you have three of them attached to a triglyceride, right? If they're saturated, they stack. And so they have a really high melting point because they stick together. And so this would be like bacon grease here, right? Like you cook the bacon grease and it's liquid, and then when you turn the pan off and come back later, it's like hardened into that solid bacon grease. The reason it's solid is because those triglycerides have linear saturated tails, and they just stack really well and make a nice rigid solid. On the other hand, your oils tend to be unsaturated triacylglycerols, meaning that the fatty acid tails have those cis double bonds, and so they're kinked and they're bent in all different directions. And if you try and pile them up, they don't really stack well and they tumble, which is what a liquid is. And so the amount of double bonds kink the tails, they don't stack well, they tumble, and they're liquidy. So fats are saturated, oils are unsaturated. Now, here's a chart that you don't need to know whatsoever, but I thought you might find it interesting. It's showing you the relative composition of polyunsaturated versus monounsaturated versus saturated fatty acids within different types of food sources. And so things that tend to be solid at room temperature, like beef tallow, butter, coconut oil, if you look, they have a higher percentage of saturated and monounsaturated fats, and they have almost no polyunsaturated. Whereas on the other hand, if you look at plant oils like olive, canola, soybeans, sunflower, safflower, corn oil, they all tend to have a lot more polyunsaturated fats, which have a lot of kinks, which makes them oily and liquidy. Now, coconut and palm oil are like a weird exception. They're almost exclusively saturated, but they come from plants. Most plants make unsaturated fats. For some reason, coconut and palm trees evolved to have saturated fats. It is what it is. But otherwise, usually saturated fats come from animal sources and oils come from plant sources. Coconut oil and palm oil are like the oddballs. So let's talk about hydrogenation of a triacylglycerol. So a hydrogenation reaction is the process of adding hydrogen onto a double bond. So wherever the double bond used to be, we're going to be adding hydrogens to it. And so 4, 5, 6, 1, 2, 3, 4, 5, 6. So like we added hydrogens there and there. And in doing so, the double bond became a single bond, right? Over here, we had hydrogens. That's where they went. Three. And so we added hydrogens into the tail, and the double bonds became single bonds. And so we took our unsaturated oil and turned it into a saturated fat. Now, this requires bubbling hydrogen gas through hot oil, and you usually need a catalyst, like a nickel catalyst or a platinum catalyst. This was patented in like 1905, the hydrogenation of vegetable oils on a commercial scale. And you may ask, like, what's the purpose of that, right? Like, why do we want to do that? Well, some food products are considered more desirable if they're creamier as opposed to liquidy. One of the most common ones is peanut butter. So if you've ever seen organic peanut butter that sits on the shelf for a long time, all the peanut pieces settle and the oil rises to the top, and you have like peanut oil and peanut solids. And when you get home, you gotta like stir it for 10 minutes, and it's like kind of annoying. Whereas the mainstream peanut butters, like Jif or Skippy or whatever the classic ones are, they never separate no matter how long they're on the store shelf. They're always this same unique, like uniform creaminess. And the reason is they took the peanut oil with the unsaturated double bonds and they hydrogenated it commercially and turned it into a saturated fat. Because the saturated fat is solid at room temperature, it never really melts. And so you went from peanut oil to like peanut butter, essentially. And so this was, like I said, patented in 1905, and they started hydrogenating everything. You had fake butter, you had Crisco, margarine, you had no stir peanut butter, and you had all these like magical alternatives to natural things. And they did this for, the last 120 years. Well, one of the things that they realized is that every once in a while, instead of adding hydrogen and making the saturated fat, the cis double bond can isomerize into a trans double bond. This isn't what they were trying to do. This was just a byproduct, but it happens every once in a while. And trans fats are more linear, so it still has the creamy consistency that they wanted, so they didn't worry about it. But what we found out like 60, 70 years later is that trans fats are extremely bad for your health. Almost all naturally occurring fats are cis, and your body recognizes that bent shape. The trans fats don't get processed by your body's metabolism in the same way because they don't have the same bent shape that your body is used to. And these lead to plaque buildup in your arteries, high blood pressure, early heart attacks. They're really bad for your health. They're like the worst type of fat. And it's sad because they almost don't naturally occur. We made them artificially through an industrial process. We didn't foresee what we were doing, and we did it for almost 100 years before we realized our mistake. And so nowadays we're phasing it out. You don't really see hydrogenated oils in as many products. It's completely illegal in Europe, but America has less health standards than Europe. And so we still do it in a lot of food products. So if you see the word trans fat on a nutrition label, you do not want it unless the number says 0, right? But they're kind of tricky. So even sometimes they'll say 0 trans fats, but if you read the listed ingredients, it'll say hydrogenated oils. Anything that's hydrogenated is going to have some trans fats in it. So you really want to avoid hydrogenated vegetable oil or partially hydrogenated vegetable oil. That refers to this chemical process, which in and of itself isn't that bad, but the byproduct of it are trans fats, and those are really bad for you. Also, a lot of these polyunsaturated fats are essential fatty acids that your body really does need, and you're destroying them by turning them into saturated fats. So even if they're not trans, you're destroying the really healthy essential fats. So really, you just want to avoid hydrogenated oils in general. Moving on, let's talk about hydrolysis of triacylglycerols. So you can do the hydrolysis using an acid catalyst or with digestive enzymes known as lipases. This is what happens in your body. And the ester bonds are shown here in red. And so we're going to add water, and we are going to cut those ester bonds. And we're going to add the waters back in. And when we do that, you end up with the glycerol and the 3 fatty acid tails. All right, so sort of the opposite of the formation, right? Formation is the esterification, where you're combining the 3 fatty acids with glycerol. Hydrolysis is taking the triglyceride and cutting it to release the glycerol and the 3 fatty acids again. Now, this is using an enzyme or an acid catalyst. Recall that we could do hydrolysis using a base. This gets a special name called saponification. And so it's hydrolysis using a base like NaOH. Now, if you recall from chapter 12, when you use a base to do the hydrolysis, you still cut in the same place, but we don't have H2O anymore. We have H and we have NaO. And so one side gets the H, the other side gets the ONA. So the glycerol gets the H, and the fatty acid gets the O- with the Na+. This is known as the carboxylate salt. We learned that in chapter 12. Now we have the carboxylate salt of a fatty acid. The carboxylate salt of a fatty acid is soap. Yes, like hand soap that you wash your hands with. This is a soap molecule. It's the carboxylate salt of a fatty acid. And this is how we have traditionally made soap for thousands of years. We take oils, triacylglycerols, we mix it with sodium hydroxide, and we do this base catalyzed hydrolysis, also known as saponification, or as I like to remember it, soaponification. That helps you remember it, right? It's the process of making soap. And we get our 3 soap molecules and glycerol. Glycerol floats, and you can skim it off the top, and then you just leave behind the fatty acid salts. And so here's an image showing you taking olive oil, which would be something like this. You get your your three sodium hydroxides. We're going to cut the esters. We get the glycerol and the three soap molecules, which will harden and turn into a bar of soap. You can do this in a chemistry lab. We actually do it in Chem 5. We take olive and coconut oil, we add some sodium hydroxide, and the next week the students have a bar of soap to take home. It's a simple reaction. So let's talk about these soap molecules real quick. The soap molecules have a polar head region. And when I say polar, I really mean like it's ionic. It's got a positive and a negative charge. It's ionic. This thing really wants to dissolve in water. It's ionic. But you also have this long non-polar tail. This part really doesn't want to dissolve in water. And so you have this dichotomy here, this fighting of forces. This part wants to go in the water, this part doesn't. And so what happens is when you dissolve these in water, they form this three-dimensional structure called a micelle that looks like this. Now, your soap molecule has the polar head and the non-polar tail. For the sake of drawing, we're going to abbreviate it as this cartoon where the polar head is a sphere and the tail is like this little tail. Now, these things orient into a sphere where all the heads are pointed outward and all the tails are pointed inward. And it forms this three-dimensional spherical micelle. These molecules are packed, touching, just back to back to back to back to back to back. There's no gaps in between. And the polar heads all point outward and the non-polar tails point inward. And this entire micelle dissolves in water because the entire exterior of it is polar and loves to mix with water. And so the water molecules interact with the outside of the micelle, and that entire micelle dissolves into the water. But the inside of the micelle is like a little droplet of oil. It's all these non-polar tails. Water molecules don't want to go in there, and the tails don't want them in there. It's completely excluded from water. And so this unique three-dimensional structure naturally forms as a result of the forces of the polar head and the non-polar tail when you throw it into an aqueous solution. They don't want to just be free floating by themselves around the water. They will quickly orient themselves together and form this micelle to try and get the tails away from the water. Now, the reason it cleans your hands so well, imagine if you had some other oils or non-polar things, sticky stuff stuck to your hands, and you lather it up with soap. What happens is all those non-polar molecules that were on your hands get trapped in the middle of the micelle. And then when you rinse your hands in water, the whole micelle rinses off in the water. And so that's how they work so well as a cleaning agent, is because they can trap non-polar molecules on the inside of the micelle. So if you're working on your car and you got greasy hands and you try to just rinse them with water, the water is not going to wash the grease off. But if you have soap and you lather it up, it forms these micelles and it traps the grease particles on the inside of the micelle, and then the whole micelle washes off. And so that's why it works so well for cleaning your hands or dishes or whatever. So that's how soap molecules work. Hopefully you found that interesting. So let's do a summary of the reactions. We talked about 4 reactions. Esterification, which is how we form these things, right? You take your glycerol, your 3 fatty acids, and you form the esters to make your triacylglycerol. We talked about hydrogenation, which was the process of taking the unsaturated double bonds adding hydrogen and making it saturated. And the byproduct of that is accidentally forming the trans fats. We talked about hydrolysis using acid or an enzyme. And so hydrolysis under acidic conditions gives you 3 fatty acids and a glycerol. And then saponification is hydrolysis using a base. And that's when you get your 3 soap molecules, your carboxylate salts and the glycerol. So those are the 4 reactions of triacylglycerols. And yeah, that's it for this video. Thanks for watching. I'll see you in the next one.